Welcome to SDIT online classes. I am Dr. P.S. Kushik, Principal at Sri Digambar Institute of Technology, Dosa, Rajasthan. I am taking the subject Engineering Mechanics. This is my lecture number 29, Analysis of Moment of Inertia of Composite Sections. Let us refresh our memory about MOI till now. This moment of inertia, that is mass moment of inertia and section moment of inertia. We studied about the perpendicular axis theorem, parallel axis theorem, radius of gyration, and we derived simple relations of MOI. We analyzed few cases of composite section. In this lecture, we will derive more relations for moment of inertia and take up a typical problem of composite section. This is the case of circular lamina. So, we will use the integration method to derive the relation for moment of inertia about x-axis axis and y-y axis and z-z axis. This is the circular lamina, this is x-axis, this will be a y-axis, and the vertical axis, vertical to the plane of paper, will be the z-axis. Here consider the element of side r d theta and dr. Here we have considered this lamina whose one side is r d theta and the thickness is dr. This which is distance r away from the axis x-axis. So its moment of inertia about x-axis will be y square dA, whereas y is r sin theta. This is y, basically vertical distance from the axis, it is r sin theta. This lamina having dimensions r d theta and dr is negligibly small, hence it is being shown in a enlarged way, otherwise it's a very small area. So you can virtually call it that its distance from the x-axis is r sin theta. So, and area is of this lamina is elementary lamina is r d theta into dr. Hence, replacing y square dA by r sin theta whole square into r d theta dr. Yeah, then it becomes r cube sin square theta d theta dr. The moment of inertia of whole lamina will be found out that by double integration and applying the limits 0 to r and 0 to 2 pi. Since the theta changes from 0 to 2 pi and r changes from 0 to r, capital R. So it becomes 0 to r and 0 to 2 pi r cube sin square theta d theta dr. Writing sin square theta as 1 minus cos 2 theta by 2, we can write 0 to r and 0 to 2 pi r cube 1 minus cos 2 theta by 2 d theta dr. First integrating for 0 to 2 pi, then it is theta minus sin 2 theta upon 2 0 to 2 pi in integral of 0 to r dr. Here when we apply the limits, then sin 2 theta is just sin 4 pi is 0, as sin pi is always 0, and sin 0 is, you know always that it is also 0. So the values for this will be automatically 0. So it becomes as 0 to r cube by 2 2 pi dr. 2 pi being constant taken outside, then it becomes r4 by 8, 0 to r limits. When applying, it becomes pi r to the power 4 divided by 4. If d is the diameter of this circular lamina, then replacing r by d, then it becomes ixx pi by 64 d to the power 4. Likewise, you can take for y-axis that Iyy equal to pi by 64 d to the power 4. If zz is the axis, as I told you earlier, that it is the axis which is perpendicular to the both the axes and at the point of cross section of these two axes, that is at the point here. Yeah. So it will be vertical to the plane of paper, it is vertical to both. Then, as we have studied in the previous lectures, Iz equal to Ix plus Iy. So you can say when adding these two, it becomes that polar moment of inertia becomes pi d4 over 32. This axis zz is called polar axis and Iz is referred to as polar moment of inertia, as we studied in the previous lecture also. And why we call it a polar? Because normally this a circular shaft is like this, is a circular shaft, and applied torque is applied, then we say that the length of shaft is more compared to its cross section. So, and any member which have length much higher than its cross section dimensions, then we call it a pole, as similar to as electrical pole, you know. Okay, then polar moment of inertia has applications in problems relating to torsion of cylindrical shaft and rotation of slabs. For a circular lamina of diameter d with central circular hole of diameter small d, refer to figure 8.13 here, the moment of inertia about any centroidal axis is Ixx is equal to pi by 64 d to the power 4 minus d to the power 4. And the corresponding polar moment of inertia will be just double of that is pi by 32 bracket d to the power of capital D to the power 4 minus small d to the power 4 bracket close. So this is the relation for circular lamina. And then moment of inertia of a semicircular lamina now. That is half circle, this much. Now, as we know that the moment of inertia about this axis is pi by 64 d to the power 4 as shown here. So half of it will be, for half lamina about this same axis will be pi by 128 d to the power 4. But if you want to know its centroidal axis for half circle, this is a half lamina, its centroidal axis will be here somewhere, which is about 4r upon 3 pi from the base. This AB, its centroidal axis will be here, which is 4r upon 3 pi away from the AB. So here we can apply parallel axis thought to find the relation, or we can go with the first principles and applying the limits from 0 to r and 0 to pi, because limits 0 to pi here, then you will find that IAB comes out to be pi d to the power 4 upon 128, that is half of the complete circular lamina. Now, for centroidal axis IXX, we can apply that IAB equal to IXX plus y square A. So, IXX will be IAB minus y square A. A is the pi by 2, sorry, pi by 2 r square will be the area, and in terms of d, it will be pi by 8 d square. So, you can say area of the semicircle, half of pi by 4 d square, that is pi d square by 8, and applying this equation, this condition, the parallel axis for that, this is IAB, this is IXX, and this is the y square A. Then on calculation you will find that IXX comes out to be 0.00686 d to the power 4 or 0.11 r to the power 4. This is the relation we will call. Now, consider the simple problem. Here in this problem, he has given IX and IY and want to know the dimension of a rectangular lamina as shown in the figure. Here, the moment of inertia of rectangular section beam about x and y, xx and yy axis passing through the centroid are 250 into 10 to the power 6 millimeter 4 and 40 into 10 to the power 6 millimeter to the power 4 respectively. Calculate the size of the section. We want to know the dimensions of the section. It is a very, very simple problem that we know IX, this is B, this is D. So, for IXX, BD cube by 12 here, writing BD cube by 12 equal to 40 into 10 to the power 6 here. Then IYY is DB cube by 12, and again writing here the values here, and then dividing first from second, then you will find 5.25 equal to D upon B square, or D by B equal to 2.5 here. Substituting value of D in terms of B in equation first, we find B by 12 equal to 2.5 B to the power cube, then is equal to 250 into 10 to the power 6. Then on solution, it comes out to be that B to the power 4 equal to 1.92 into 10 to the power 8. That gives B equal to 117.7 millimeter, and putting the value of B in any of the first or second, you will find that D equal to 2.5 into 117.7, that comes out to 294.25. Therefore, the required size of section is B equal to 117.3 and depth equal to 294.25 mm. This was a simple case. Now, this is a typical problem. In this problem, we have to find the moment of inertia about the centroidal axis, which is shown here. For that, first of all, we have to find the centroid. Then we will find the moment of inertia of respective laminas, and then we will apply the parallel axis thumb to transfer the moment of inertia at the centroidal points. So in this case, first is define the reference lines. These are the left hand edge and the right hand edge. Sorry, left hand edge this and the bottom edge as the um, reference axis for the centroid to be known first. So, and break this L section into two rectangles which has been broken there. Section 1 is this much and section 2 is this much. So first y bar, that is y coordinate of the centroid is a1 y1 plus a2 y2 upon a1 plus a2, and x coordinate is a1 x1 plus a2 x2 upon a1 plus a2. So x1 on calculation, that is 20 into 10, that is the area. 20 into 100 is the area, and the centroid point of section 1 is 10 mm away from the left edge. Similarly, the centroid point of the section 2 is 50 mm away from the left edge. Similarly, for y coordinate, the section 2 is 50 mm away, whereas section 1 is 50 mm away from centroid point is 50 mm away, whereas for section 2 it is 10 mm away from the x. This is bottom edge. So applying this, we find that x bar comes out to be 25 mm. That is, it is 25 mm away from the left edge here. This much distance is 25 mm. Now similarly, for y bar comes out to be 35 mm. Means it is, this distance is 35 mm. Now h1 means this distance is h1. Which is 25 minus 10, 15 mm, S2 50 minus 25, 25 mm. Similarly, Z1 15 mm and Z2 25 mm. Hence, now applying the parallel axis theorem for this, we know that IXG, XG means this centroid axis is, you can say GG, XG, XG is this one. So, this is the x dimension is like this. So, I gx1 plus a1 h1 square, I gx2 plus a2 h2 square. Similarly, iyg, I gy1 plus a1 z1 square, I gy2, then a2 z2 square. Gy1, this that centroidal moment of inertia of lamina 1 about this axis here, which will be for y, about y, that will be how much? D. This is axis, so 100 into 20 cube by 12. About y-axis, I, G, Y1. Hence, now finding the Ixg first. Ixg equal to Igx1 plus A1 H1 square plus Igx2 plus A2 H2 square. Applying for x, this is the x, xg, the red line is shown here. So, for section 1, this is the axis for it, so it will be 20 into 100 cube. Cube is done for the dimension which is perpendicular to the axis of reference. So here we have done the cube of 100 divided by 12 plus its distance from centroid, square of the distance from centroidal point, this much distance, which is equal to h1. This is 15 mm. So 15 square into area, 100 into 20, 100 into 20. Then for section 2, its area is 60 into 20 because this much is removed from here. So 60 into 80 minus 20, 60, that is. So 60 into, first 20 is the area, then and this is the axis of this of reference. So cube will be done of the 20 mm dimension. So here 60 into 20 ka cube divided by 12 plus this distance is 25 mm. This distance is h2 is here h2 is given 25 mm. So 25 square into 60 into 20. On calculation, it comes out to be 2.907 into 10 to the power 6 millimeter to the power 4. Here 4 is missing. Millimeter to the power 4. Now for YG, same case, so IGY1 plus A1 Z1 square plus IGY2 plus A2 Z2 square. For the dimension, similarly, take the dimensions again. Here, this is the axis. This is the axis for this, and this is the axis for this. This distance is Z2 and this distance is Z1. Okay, so let us proceed now. Z1 is 50 minus 35, 15 mm. Z2 is 35 minus 10 is equal to 25 mm. So cube is done of this dimension for the section 1. So 100 into 20 cube by 12 plus 15 into area, 15 square into area, that is 100 into 20. Similarly, for this section, that is area 2, that is cube, because we are doing this, the cube will be done of this dimension, that is 60. So 20 into 60 ka cube by 12 plus this 25 square, this is square into area, 60 into 20. On calculation, you can take a calculator and proceed it comes out to be 1.627 into 10 to the power 6 millimeter to the power 4. I think let us recollect it what for this problem again. What we have to do is for this problem, what we have to do first define the reference lines. We have defined here the left edge and the bottom edge. Then break this lamina into two typical shapes. That is, here we can say that it is rectangles, two rectangles, that is rectangle 1 and rectangle 2. We have broken it virtually. Now first find the moment, the centroid of these laminas which are at the cross section of their diagonals. So you cross the diagonals, it is one here, the diagonal of here, this is here. So this is brown dots shown here. Now find the centroid of the complete lamina, that is L shape जो lamina है इसका complete का, by applying these two thorns. Now find the distance of these centroids from the common centroid. Find the distance of this section 1 and section 2 centroids from the main centroid, that is common centroid, from here to here. This distance we have to find out. Then this distance we have to find out. Similarly for this axis we have to find this distance. Similarly we found that for x dimensions we call them h1 and h2. These are 15 mm and 25 mm like this. For y dimension we call them z1 and z2, which are 25 mm and 15 mm. Then apply this formula, this one and this one, to find the moment of inertia about x centroidal axis, this, and y centroidal axis, this. That's all from my side. Thanks for watching this video. We have referred the books Engineering Mechanics by Dr. D.S. Kumar and Engineering Mechanics by R.S. Kurmi and Google search engine. Thanks for watching.